So we are going to look at the forms of energy and changes, PhET simulation. So in this simulation, we have two components. We're going to look at the intro, and it's very interesting to see how this works. So here we have a couple things, and what we're going to do, and the best part about the simulation is it's going to use this E to represent the thermal energy contained within iron, brick, water, and oil, and we'll be able to change the temperature of each by either cooling them down or heating them up. So the first thing I want you to do is I want you to predict. So we have water. I'm going to put that here, and I have oil. I'm going to put that here. And I want you to predict. And I'll just say I have the brick here. No, I guess I put it here. Okay. Which of these, water or oil, will have more thermal energy, or will they have the same amount of thermal energy? And the same is true for the iron and the brick. So which will contain more thermal energy? Now, what I will say, before you make your prediction, if we check out the temperature, so if we come here, check out the temperature of the water, check out the temperature of the oil, check out the temperature of the iron and the brick, you can see that they are all at the same temperature. They are all at room temperature. So all four of these have the exact same temperature. Now, you can see that the iron and the brick have similar, we don't know if they're the same mass, but they do have the same, they're about the same size. Again, water and oil have the same volume. So do they have the same thermal energy if they're at the same temperature? And the answer is no. So remember how I said that thermal energy and temperature are not the same? And we can see that here. We can see that water has a lot more of these little E's representing more thermal energy than the olive oil. Olive oil has a lot less. So even though they have the same temperature, water contains more thermal energy. And the same is true here. Iron has more thermal energy than the brick. And so what that means is that iron has a higher specific heat capacity than the brick, and water has a higher specific heat capacity than the oil. And the best way to see that is if we have these here, and we can heat them up and see how temperature changes. What I'm going to do is I'm going to link the heaters together so I add the exact same amount of thermal energy. And so if I heat both up and we are adding the E's at the same rate, and we see what's happening with the temperature, so we're adding thermal energy, and we can see the oil is changing its thermal energy at a much faster rate than the water. So if I bring it back down, you can see that the temperature is much higher for the oil than for the water when I add the same amount of thermal energy. That means that the oil has less resistance to temperature change when adding a specific amount of energy. So specific heat capacity is the amount of energy required to change 1 gram of a substance 1 degree Celsius. And so if I add the same amount of joules to both water and oil, there is more resistance of the oil. Now you'll notice as it's cooling down, and I can force cool it a little bit, that the oil changes its temperature, cools down much faster than the water in the same way. So it is least resistant to the change in temperature water is. Okay, so let's do this. Let's bring this here, and let's take the water. We'll put it over here. So that's the first thing, that temperature does not tell you anything about thermal energy, and that things with higher specific heat capacities have the ability to store more thermal energy. And this is very true. We see this application of this all the time. So things that have even a higher specific heat capacity than water is something called ethylene glycol, which we use as antifreeze. And this solutions that have ethylene glycol are even more resistant to temperature changes, such as they won't freeze when it's cold outside. But the brewing industry uses these a lot. The brewing industry has a lot of cycles that involve heating up large amounts of a solution as well as cooling them down. And so they use ethylene glycol as a way to basically store thermal energy from one cooling cycle to the next heating cycle of another batch of beer. And so we can store a lot of thermal energy within water or things like water. So let's get this iron. Let's get this really hot. So we're going to add some thermal energy here. And we can see what happens. So we're going to put a bunch of thermal energy in here. Let's see what temperature we're at. Let's get it, go up, up, up. And what we're going to do is we're going to take this iron and we're going to put it into the water. Okay, we're going to take this, put it into the water. And we'll see, look how much quicker the iron's temperature goes. Then that was a little fast, I know, than the water. And now we've reached thermal equilibrium between these two substances. So they both have the exact same temperature. But we can see that the final temperature is much closer to water. That happened a little fast, I realize it. And so let's do this. Let's show the same principle with a brick and the iron. So we can go and heat this up as well. Oh, that was over here. Okay. And we'll get this here. Okay. Out of the way. Now, okay, so now we're going to link the heaters together. We are going to, let's cool the iron down a little bit. Oh, I guess I can't link these. Let's get them the same temp. Let's bring this up a little bit. There we go. Okay, link the heaters, and let's watch what happens when we heat them together. We should see the brick increase in temperature faster than the iron, based on the prediction that it has a lower specific heat capacity. And if we pause it, here we can see that, yes, the brick is least resistant to thermal energy or being added. The temperature changes at a faster rate than the iron, which means that if you add the same amount of thermal energy, so we hit play, that the brick will be warmer than the iron. Now, interestingly, see how this temperature here is way up here? Now, if I want to get the iron to that temperature, I need to add a bunch more thermal energy. And so we're gonna play. We're gonna do that. So if I want to get this up to the same amount as the brick, then I must put in a lot more thermal energy. So things that are at the same temperature, to get iron to the same temperature as a brick, I have to add a bunch of more thermal energy to the brick. And that's why when we started at room temperature, we had the more thermal energy in the brick and more thermal energy in the water, because it took more energy to get it up to the room temperature. Okay, so this is a very useful to kind of show you how specific heat capacity relates to the thermal energy, and that just because objects have the same thermal energy does not mean, or sorry, the same temperature does not mean they contain the same thermal energy. And the amount of thermal energy that a substance contains is directly dependent on the specific heat capacity of that substance, where the larger the specific heat capacity, the larger amount of thermal energy can be stored in that substance, and the more energy is required to change that substance's temperature per gram of that substance.